All right, so I've been learning C++ for a while now, and I have a pretty good idea of what it is and a lot of notes. So I've decided to share with you guys about a month of C++. Pretty much what you can expect to learn on your first month of learning C++. It's basically going to be variables and basic types. So let's get into it. The first topic we're going to do is compound types. Now, compound types are basically references, pointers, references to a pointer, pointer to a pointer, the null pointer, a void pointer, and operators such as the address of and dereference. So let's get it started. First, let's start off with the reference. A reference you can basically think of a reference as another name or an alias for an object. So let's write that down. Reference. Name for an object. To separate name for an object. Now, this would basically look like you have int x, and then you would do a reference to an int, and then let's call that r, and then you would seat that to x. Now, r is basically just a reference to x, uh, defined by this address of operator right here. Then we can do a pointer. Pointer is just an object in itself that stores the address of another object. So we can write pointer object that stores address of an object. And that would basically look like we have int x, and then we would have a pointer to an int noted by the dereference operator, call that p, and it will store the address of x. Now, next we have a reference to a pointer. A reference to a pointer, that's just an alias for a pointer. Pointers are objects in themselves, and references are aliases for objects. Therefore, we can have a reference to a pointer. So let's do reference to a pointer. To pointer. And that's just an alias for a pointer. Now let's use this p example, this pointer p example. We would just do a reference to a pointer of an int would be an int. And we can just call this reference to pointer, denoted by the ampersand, equals p. And there we go, we have a reference to a pointer. Now let's do a null pointer. Yeah, let's do that. What is a null pointer? Let's see. A null pointer is basically a pointer which points to nothing. It is of itself its own type. It's not a pointer as, just a regular type of pointer. A null pointer is still null pointer. So it is its own pointer type. Let's do null pointer. Empty pointer that holds nil. And we would denote that with int pointer, call that p equals null pointer right here. This is the syntax for null pointer. Now let's see what else we have. We have as well void pointers. Now a void pointer is a pointer that can point to any non-const type. Void pointers cannot be dereferenced because the pointer does not know the type of object that is being stored. Therefore, it doesn't know which operations are allowed on said object. So let's write void pointer can store any non-const type and cannot perform operations. So let's say we have int x, and then we have void pointer VP is going to hold the address of x. And remember, we cannot perform operations on x from pointer VP because the void pointer has no idea what type is being stored. Next, we're going to do the address of and dereference operators. Now, these are pretty simple. We've kind of talked about them throughout this explanation, but in simple terms, the address of operator yields the address of the object to which it is applied to. And the dereference operator, dereferencing a pointer returns the object to which the pointer points. So applying the dereference operator to a pointer, you're going to get the value that is stored inside of the object stored inside of the pointer. So let's start off with our reference operator. Yields address of object applied to. So let's say we have int x. And we want to get the address of x, we just do address of x, and that will give us some number 00006. That would be the address. Now if we do the dereference, which is the asterisk, as I said before, it returns the object to which the pointer points. So we would get what is stored inside of the object stored inside of a pointer. So returns object stored at address inside of a pointer. So if we do int x, and then we do pointer to an int p equals address of x, and then we dereference p, we would get, well, let's initialize this actually. Let's initialize it to 420. Let's do 67. 67. Dereferencing p would give us the value stored inside of x. So dereferencing p would give us 67. Now those are compound types. I hope that helped you guys. Simple explanations. GG's. Let's go on to the next topic. All right, so video number 2. This one's going to be on floating point, precision, and range. So for starters, floating points are numbers and they're stored in normalized binary scientific notation. And that pretty much means that they are comprised of a significand and an exponent. The significand is it's the binary digits to the right of the decimal point, or basically how many it can hold. So for example, we have 1 and then point. The significand, the binary digits would be however many x's can be held on the right side of the decimal place. Now the exponent is given we have 1x point xxx. The exponent would be how many places we need to move this decimal point so that all the binary digits are to the left of the dot. So for in this example, the exponent would be 3. Exponent would be 3. And then the fundamental representation of a floating point number can be evaluated to the significand times 2 to the power of the exponent. And this is also what's known as mantissa, I believe. And this is how floating points are evaluated. Now, there's 4 main parts when it comes to evaluating floating point values. We have first range. We can think of this as the extreme positive and negative values. And if you want a more simpler explanation, think of it as your number line. So extreme, negative, and positive values. Your number line. And then we have magnitude. And these are, or I guess the magnitude of a number, the magnitude of the floating point would be the floating point number itself, or the size of the individual value. You can think of this as the position of the value on the number line, or its length from 0. So if we have another number line, we have 0. A magnitude would be right here, let's say 5, and a magnitude right here, negative 5.0. Then we have precision. Precision for a floating point value are the fixed significant bits for the specified type. And in our number line example, it would be how many ticks there are on a number line. So we can put fixed number of significant bits. For specified type. A float is 2 to the power of 23 and 2 to the power of 24. And then a double is 54. No, 53, I'm pretty sure. 53 or 54. It's one or the other. 53. 54. One or the other. Yeah, it's 22. Okay, I'm pretty sure this is 23. You know what? It is what it is. What else? And then after precision, we have the gap, or the ULP. Now, this gap is the gap between consecutive integers. So, gap between consecutive integers. And you can think of this as, let's see, the spacing between each tick. So let's go back to the precision example. Let's say we have a number line. The precision is the number of ticks on a number line. So ticks. And then the ULP would be the spacing between each tick. So at some point, the spacing would become even larger. Now let's bundle all of this information up together. Let's say, let's put an example here. Yes, put an example here. So let's say a double has 53 bits, precision bits. So double, 53 precision bits. And that means that it can represent every consecutive integer up to 2 to the power 53. Now remember, I told you, floating point value is evaluated by the significand times 2 to the power of the exponent. So in case of a floating point, a double, that exponent would be 53. So 2 to the power of 53. And we can think of this gap as intervals. So in the interval 2 to the power of 53 and 2 to the power of 54, the gap between consecutive integers would be 2. It would be 2. Meaning that whatever 2 to the power 53 is evaluated to, if you add 1 to it, C++ is going to return that original number. It won't be the next consecutive integer, because after a certain point, after a certain magnitude, the consecutive integers that are representable is doubled in this specific interval. So let's just say this was 9, and then we tried to do 9 plus 1. We would get 9 back because the gap is double. We cannot evaluate a value that does not exist or cannot be represented. So, our rule note would be let's highlight this, as the exponent increases or shifts to right, by 1, the spacing between representable integers doubles. And if you want an equation, each interval can be represented as 2e, the exponent, and 2e plus 1. And for a specified type, they contain the same number of representable values. Sorry, I shouldn't say contain type. I guess I can say that. So, let's do some interval examples. As I showed you guys before, 2 to the power 53 and 2 to the power 54. We get 2. And according to this equation, we can do 2 to the power 54 and 2 to the power 55, and our gap would double. It would be 4. And then we can do 2 to the power 55 and 2 to the power 56, and that would double. So this is pretty straightforward. So before I close off this video, I want you guys to guess what the next value would, the next gap would be for this interval. Put it in the comments. I hope you guys learned a bit about how floating point values are represented. And GG's, let's go to the next topic. Alright guys, this topic is fairly short. We're gonna do signed versus unsigned. So for starters, signed can represent both negative and positive values, ranging from -2 billion to about +2 billion. So signed, negative, positive, and the range is -2b to +2b. And then we have unsigned. These can only represent positive values only. And because they can only represent positive values, the range doubles from 0 to about +4 billion, I think. But some of the behaviors on what happens with these is implementation defined. So whatever happens on your system, it might not happen on another system. That's a good thing to note. And for unsigned arithmetic, when you mix them, something funny happens. When they're both in an expression, so let's say you have int x equals 1, and then you have unsigned y equals -1, and then you want to do a comparison. What's the comparison? Is y greater than x? So this is what happens. In an expression like this, or when signed and unsigned is mixed, the signed value is going to be converted to unsigned type. So essentially, we get unsigned compared to unsigned. But the tricky part is unsigned values can only represent positive numbers. So when we have a negative, for example, in this case, -1, we have something called unsigned wraparound. And this will convert to, if we start at a negative value, first is going to convert to ui int max minus n minus 1 minus n minus 1. So in this case, we get ui int max minus 2, I believe. Yeah. So in this case, what this expression is going to evaluate to is it's going Yeah, the expression is going to evaluate true only because UIN max is a very large number, and a very large number is obviously bigger than 1. So that's just something to keep note of when you're dealing with signed and unsigned types. Since unsigned can only represent positive values, when you go to a negative value, it wraps around to the highest possible value for that specific unsigned type. And then when it comes to overflow and underflow, signed overflow will always be undefined behavior. Undefined behavior. And that is because the compiler is allowed to assume that you're never going to go over the max value for a specific type, integer type. So we just define that as undefined. And so we can assume it never happens. And that's basically what undefined behavior means. The compiler is safe to assume that it's never going to happen, and if it does, well, we'll just see what happens. Now, unsigned overflow is in fact defined. And it is defined by mod 2n arithmetic. And this is also wraparound. And where n is the number of bytes number of bits or number of bytes. I'm not sure. Pretty sure it's number of bytes for each type. Yeah, number of bytes for a given type. And that is signed and unsigned integers. Pretty simple. On to the next topic, GG's. Okay, for our next topic, we're going to be doing variables. Now, for starters, variables control 4 things. They control type, they control lifetime, they control scope, and they control initialization. Now, the type controls the size of a variable. They control the range of a variable. And they control the conversions between variables. Lifetime determines how long the object is active in memory. So, how long the object is active in the memory. Most variables within your program, for example, int x inside the main, those would be stored inside the stack. Your scope is where a variable name is visible. Where a variable name can be seen. There's different types of scopes. There's inner scope, which is a scope that is nested inside of another scope. There is local scope, which is another name for a block scope. Kind of like main, kind of like when you have a for loop. The body inside of the for loop, the code that is to be run, is the block scope. What else do we have? And we have initialization. So what it means to be initialized is the object is defined with the value at creation. That can look like int x. Sorry about that. Int x equals 0. So object defined with value at creation. And remember, scope is just curly brackets, pretty much. Those are bad curly brackets, but you guys get the point. Now let's discuss declaration versus definition. So declaration versus definition. So the definition basically consists of the type. It has the name and maybe linkage. And that would look like using extern, but that's for another video. And then a definition, just note this, dec and then def. A definition is the type, it's the name, it's initialize, it has an initializer, it has an initializer, it has a value, and as you can see, a definition and a declaration, they kind of have similar values. They have types, they have name, and that's about it. So, as you guys can see, a definition is basically just a definition is just a declaration with storage and with initialized storage. So it's plus a definition. Declaration and definition can be one. A definition is a declaration. It's a declaration with storage and an initializer. Now, before we finish this off, here, let me move this. That doesn't really do anything. There are two types of object lifetime durations. So we have static, and that pretty much means that the object is declared at the global scope, or it has to be declared static using the keyword, declared static at global scope, and this pretty much means that the variable has a lifetime of the program. And then we have automatic lifetime duration. And this pretty much means that the object was created inside of a function body. So inside of a for loop, inside of main, inside of a if statement, anything like that. Inside of an internal scope, that gives it an automatic lifetime duration. Its lifetime is the lifetime of that scope, from the line it was created to the closing bracket of the scope. So we can write created inside of a function, inside func lifetime of scope and when these values are not initialized, they have indeterminate values, and that pretty much means they store junk, a junk value or junk address. So we can just write indeterminate. Let's just put junk. Uninitialized leaves us with junk value. And that is types. I hope that made sense to you guys. And let's go on to the next topic after this. GG's. Alright, this topic is going to be on literals. Okay. Now for this one, we're going to be talking about character and string literals. So character literals are of type char. And an example we can give it is a single character A. And this has the size of 1 or 1 byte. Then we have a string literal. Now for strings, strings in C++ are pretty much pointer to char arrays. So we have a character pointer, and it's an array. And an example of a string or a character array would be the double quotes, the character. But it's good to note that if we were to get the size of this string character array, we would get 2. And why is that? That is because character arrays, or strings specifically, they're not only the character inside of it, but they succeed. The entire array ends with a null pointer, not a null pointer, a null terminator, a null terminator. So let's say we had an array of A, B, then this would actually be A, B, and then null terminator. So size of would be 3. If we get the length of this string array, then it would just return the length of all the characters, excluding the null terminator. Now let's move over to promotion. And promotion is pretty much when, let's say a lower tier value, let's say a character, is going to be upgraded to the next character, not next character, is going to be upgraded to the next type. So specifically for characters, they get integer promotion. So in arithmetic, characters are not literally, they're typically converted to an integer. So that's pretty much character promotion. They just get converted to integer. Converted to integer. And then we're going to talk about some suffixes. Suffixes. These are pretty much succeeding characters. And they're usually placed at the end of the value that you're given to a variable. So let's say we were to have an integer, int x equals 27. If we wanted it to be unsigned, we would do u. Now this is an unsigned int. We can also do capital U. Let's say we wanted to make something a long. We can do int y equals 67, and we can do L or capital L, but it's usually better to use capital L because the lowercase l sometimes looks like a 1. We can also do long. So if we do int z equals 420, we can do long or ll. I'm just going to do long. Yeah, these are what's described as integral suffixes. And there's also floating point suffixes. So the default type, I'm just going to write this, default type for floating point is usually a double. Not usually. I'm pretty sure it is. You guys can't see this actually. So the default for a floating point type is a double. So in that case, if we wanted to make something a float usually, we would have to do float x equals 1.0 and then f. We can also do capital F. We can also make something a long double. So we can do double y equals 2.0. We can use an L or an L, but as I said before, use a capital L just for clarity. And this makes this a long double. So we can denote these as floating suffixes. And then the final topic for this section is going to be escape sequences. So let's write that. There's many. We have, let's see, we have new line. We have tab. We have backslash, I mean. We have single quote. We have double quote. We have a hex value. And then we have an octal value. And we'll cover these two last. So for a new line, all you have to do is \n for tab, \t. For the backslash, it's double backslash. For the single quote, it is \, single quote, double quote, same thing as single quote, \, double quote. And then for the hex values, it's the \, and then you start it with an X, and then the character code for it. And this would give us a new line. So this is the same as \n. And then for octals, it's the \, and then the octal number. So let's do 101, and this will give us the character A. These are literals in C++, simple explanation, and let's go to the next topic, GG's. Alright guys, this topic is going to be on the const qualifier. So for starters, const usually just restricts writing. It just restricts the write access path. You can still read from it. And when you use a const as an initializer for a non-const object, you're usually just getting a value copy. So you're not pointing or referencing that original object. You're just getting a value copy. So const to non-const, copies the value. Now there's also, what else do we have? We have a reference to a const. So let's write ref to const. Now, reference to a const is a reference that doesn't change the value of the object that it refers to, and it can be bound to a const object, a non-const object. Yeah, so it can be bound to a const and a non-const object. Let's see. Let's write can bind. It can bind to a non-const, const plus non-const. It's the same object. Remember, a reference is just another name or an alias for an object. So a reference to a const, you are getting the same object with read-only access. And the object itself, not the reference, the object itself is mutable. But only if you are referencing through a non-const path. So object is mutable through non-const path. Then what else do we have? We have a const to a pointer. What is this? A const to a pointer, all it does is restrict the receding of the pointer, meaning that whatever the pointer points to, it cannot point to anything else. But I guess it shouldn't be a const to a pointer, it's a const pointer. So restricts pointer recede. And then const on the pointee, which is the object pointed to, restricts riding through the pointer. So this would look like const pointer, and then this would look like a pointer to const int. So now let's talk about top and low level. A top level const is a const applied to the object itself. Now there's different types of objects. Pointer is included as one of those objects that can have a top level const. And copying on the pointee, which is the object pointed to, not the object itself, the pointer object itself. Copying, so when you copy into a new object, the const is not preserved to that new object, and neither is a reference. So a top level const is dropped when copied into a new object. All you're taking is the value. You're not taking the constness, the referenceness, any of that. So copying to a new object, that leads to dropped const. And then for low level const, This is a const applied to the object pointed or referred to. So const on pointee slash referred to. And for a low level const, the const is preserved. Across copies. And this is because a low level const, since it's on the pointee, let's say we were to do const int x equals 420. This is a top level const. And then we were to make a const pointer p, which is going to take the address of x. This pointer has a const, and because this pointer itself is not const, but is pointing to a const int. Forgot to add the int right here. But the point I want to make is right here we are adding a const. And then if we were to try to, let's say, make an int pointer p2, and this holds p, what would happen is we are taking away the const. And this line right here would imply that the object inside of p is mutable, but it's not. As you can see, the object inside of p is a const int. So this would be ill-formed syntax. We cannot do this only because we can add a const, but we are not allowed to remove a const. And so const cannot be implicitly dropped. Be implicitly dropped. And for the final topic of the section, we will be talking about the const expression, or const XPR. Const EXPR. Now, a const is not a constant expression. Let's first get that out the way. Const does not equal const expression. For something to be a constant expression, it requires the const XPR keyword on the declarator. It requires the const XPR on declarator. And a const expression pointer requires an expression address. And a constant expression is pretty much a value that is known at compile time. The whole point of const expression is a value that is known at compile time. So this can be anything at the static / global scope, or so static / global scope, but this is usually the keyword or the life expectancy of the object. And global is just anything that's not inside of a function body usually. And because local variables are inside of scopes, they have automatic lifetime, which means that they're inside of a function body. And by default, a local variable does not equal a constant expression. Local var does not equal const expression. Now, that's about it for const expression. I hope you guys learned a bit about the const keyword. That's about it. On to the next topic. GG's. Alright guys, final section. We're doing type aliases. Alright. Type alias. Alright, as I said before, an alias is just another name. So in the event of a type alias, it'd be another name for a type. Alright, so let's write that down. Another name for a type. So what that means is that const on the alias would make the alias const. I'm sorry, it would make, yeah, const on the alias makes the alias const. And some good measures before we get into deduction and the different types of deduction. We should note that an alias is the first thing built. And then the declaration is applied after the built alias. So what are the two types of deductions? All right, we have auto, we have declare type. So let's first go over the auto keyword. It's usually depicted as auto x equals whatever. Some good things to note is that an auto must be initialized. So we can't do auto x. This does not work because they must be initialized. So we must do auto x equals, let's just say 6, 7. And then auto is going to be as of type int. So auto must init. And for auto, we must give it a single deduce type, meaning we can't, what can't we do? We can't do auto x equals 6, 7, and then 4, 20, no, 6, 7, and then y equals 420.0. This does not work because we're giving auto two different types, an int and a double. So must deduce to a single type, uno. In the event where we have, say we have a constant, so let's use green for that. In the event we have a const int x equals 6, 7, and then we do auto a equals x. Auto's just going to be an int. A plain auto will drop a top level const. So this in turn makes auto an int, not constant. Plain auto drops TL const, top level const. In the event of we have reference to an auto, let's say we want to create a reference for x, it would be auto ampersand reference to x. Since a reference is just another name, this would just in turn be a reference to an int, because Rx holds the value of x, auto deduces from the initializer. Therefore, it's going to be a reference to an int. And in the event we have a reference to a constant, what would that be? I'm sorry, a reference to a const auto. So const auto, and reference, let's call CX. This would be the same thing as this rule up here, where it's just a const auto or a const reference. But with a reference to a const auto, we can bind it to a temporary value since it's not expected to change. So in the event you want to just store a solid value, a hard-coded value into an auto, usually make a const, because it's not going to change. That's about it. So some quick rule notes is did auto deduces type from the initializer. Then the declarator is applied. Then declarator applied. And then auto alone cannot deduce the final type. There we go. Now let's talk about type declaration, or another type deduction form using the declaration, using the dec type. Yeah, dec type, whatever you call it. So what do I use for that? Let's use dec type. Declare type. Now, for a declare type, you can have the name inside the parentheses, which is the type name. And this will report the exact type. Then you can have an expression inside the parentheses. And this produces references. So in the event that we have a pointer inside here, this would just be a pointer type. So this would report the pointer type. And in the event we have a dereference pointer, this is the same as an expression. So it produces a reference, produces reference of type reference. Whatever type the dereference pointer is, it produces a reference to that type. So it's a good thing to note that parentheses can make the declared type produce a reference, or assuming that the expression itself is inside parentheses, change the type, change result of dec type. Now, what are the differences between auto and declare type? Well, it's pretty simple. First, auto. Simple rule note, auto drops the top and low level const. And declare type, declare type reports either the type exactly, or it produces a reference of type T of whatever is inside the parentheses. Produces exact type or reference to the type. And that is auto and declare type inside of type aliases. Hope you guys learned a lot. That's about it for this video. That's all the sections, and GG's.